And this is lecture 6, part 4, and I'm just simply going to wrap up this component of the lectures on mass spectrometry, namely the instrumentation, by giving you some simple examples of a 180-degree and 90-degree mass analyzer. In part 3, we described the three basic elements of the mass spectrometer, namely the objects to be weighed, a device to propel the objects to be weighed, and then a field of force, usually at 90 degrees angles to the trajectory of the particles to be weighed, that deflects them. And from the deflection angle, you can mathematically determine the mass to charge ratio in this particular case, or in general, you would be able to do the momentum analysis in the gravity field. But the point is, you have a deflection. From the angle of deflection, you can work your way towards a measure of the mass. One of the earliest mass analyzers, mass spectrometers, namely the Aston mass spectrometer, actually very much resembles the little cartoon Boris the Cat Cannon analyzer. So we begin with a filament, and you add your sample to the filament on one side of a barrier, and on the other side of the barrier you would have a collector, namely an electrode that takes the charges. So you have this partition platform, and the electrodes are isolated from the chamber by a slit, which tends to get rid of some of the spray, so to speak. So the sample we actually poured onto the filament and evaporated off. The electrode system is very similar to what I've just illustrated here. You vaporize the material on the electrode filament, and then you accelerate it towards the collector by applying a high voltage. So the basic circuit is illustrated below the contraption itself, and we have a potentiometer that allows you to adjust the voltage, so the acceleration. The system itself is sandwiched between two steel plates, and when put next to an electromagnet, they become magnetized and they provide the magnetic field. So to look at this from the standpoint from the side, what we've got is the original partitioned two electrodes. We're seeing one of the electrodes here, from viewing down the apparatus. There's a baffle or an aperture, and the idea is to get the ions through the baffle, almost like shooting basketballs through a hoop. An electromagnet surrounds the system and magnetizes the steel plates, giving you the field profile that's necessary to actually move the ions through the baffle. So you initially start off with a fountain of ions when you heat the filament and accelerate them. And then by tuning the electromagnet, changing the magnetic field strength, you torque the ions in such a way that they pass through the baffle. And so finally, going back to the original diagram from the side view with one of the plates taken off, you've got the fountain now directed through the baffle from the filament to the collector, and you measure the current as an indicator that you've got you've got the field balanced correctly so that the mass to charge ratio can be measured. Because everything is stationary, you know the radius of the turning that needs to be achieved to get the ions from filament to collector. And so once you have established the field strength, then you can determine the mass to charge ratio because of the relationship. So experimentally, you coat the filament with a salt solution, and then so the stuff is already ionized as a result. And in the article I read about this, they use saliva as the adhesive for the salt. The heating of the filament volatilizes the salt, and then you use the high voltage to launch it in the direction of the baffle, and then use the magnet to tune it. So now we'll look at a 90-degree analyzer, and the principles are somewhat similar. a little bit more nuanced in terms of the electrode facilitating the beam direction. So the power source is 500 volts in this particular version. And what we have in front of us is the ionic beam creator, or the gun. So again, we have a tungsten filament. The sample is applied to the tungsten filament, it's heated, and the ions that are already present in the solid are vaporized. There are two focusing electrodes which correct the spraying of the ions and direct them towards the slit, which is this component that's going to act like a lens. The spray comes through, and like the cathode ray tube that we saw in the previous parts of this lecture, some of the beams, some of the charged ions in the beams don't crash into the barrier, but actually pass through. And once they pass through, they're relatively collimated, meaning they're going in a straight line. So again, the lensing action. So all that remains is to sort of bend them and direct them towards a collector in a controlled fashion so that you can determine the mass to charge ratio from the magnitude of the bending force. So we introduce a magnet, and in this particular case, the magnet has a symmetric shape, so it's square or it's circular, the pole faces. And recall that in the last 180-degree analyzer, the plates acted as the magnet, and the plates had an irregular, weird trapezoidal shape. So they bent the field in a more pronounced fashion. So there remains only to have a collector, so you introduce a second slit, the Faraday cup, which is just essentially an electrode that's spread out and traps the ions that fall into it, and you measure the current resulting from the impinging ions. So this is the alternative approach, again using magnet and deflector electrodes. And this particular arrangement is found in Dudeni's article in American Journal of Physics in 1960. It's also found in the apparatus project book in the bibliography. And again, just for completion, I draw your attention again to the basic modern mass spectrometer that I introduced in the last part of this lecture, namely part 3. So if you don't have salts to work with and you want to just do neutral atoms and volatilize them, you would set up a group of vacuum chambers with the vacuum higher as you go from left to right. So the pressure is decreasing as you go from left to right. That draws the ions, or I'm sorry, the atoms or molecules through the pinhole, and they're ionized by a crossfire of electrons, namely an electron beam, becoming ionized. And once they become ionized, you can use the strategy that I outlined in the previous two examples, namely a focusing electrode and then the analyzing fields, which can be electric or magnetic. And some modern mass spectrometers have a combination of electrical and magnetic fields directing the beam towards a collector. And from the relationship of the electric field and the magnetic field, you determine the mass to charge ratio. So here's just a simple bibliography. The Blouth book is actually a very good short introduction to the design of mass spectrometers. And the two designs that I introduced in this as examples are from a book by Mark Clay, The Apparatus Drawing Project, which sort of gives you diagrams on how to build these things for a student laboratory.